Today we're going to take a look at section 4.2. We're going to continue our discussion of basically number theory. So last time in section 4.1 we were working on divisibility, and so this actually continues that idea. And specifically we're going to look at two different categories of numbers called prime numbers and composite numbers. So first of all, a few definitions. Prime numbers are any positive integers that have exactly two distinct positive divisors. So you have numbers like 2, 11, 19. Somebody give me another prime number, 13. Yep, 5. One more. 7. Cool. So prime numbers, all of these numbers divide by themselves, and they divide by 1. Okay, so those are the two distinct factors it's talking about. Composite numbers are numbers with more than two possible divisors. Positive divisors. Let me read the words that's there. So you have numbers like 6 and 10. You have like 15 and 32. So somebody give me a couple more. Let's do 2 more of them. 12. And what? 22. So there's infinitely many in these lists, right? I mean, these lists go on. We could continue on if we wanted to. Probably the rest of class period. Not necessary, but we could. And then factorization is any expression of a number in factored form. So I'm going to give you one that you might not have thought that I meant initially, but if you had the number 12, one factorization for 12 is 4 times 3. You might be looking at that and saying, well, that doesn't look like it's completely factored or something like that, but that's not what it's describing. It's just a breaking down of the number into factors. That's factorization. Now, specifically, when you think of something being completely factored, you're probably thinking of what we call prime factorization. So in prime factorization, we break things down until there's only prime numbers in the list. So if I used that same 12 that I did before, the 4 and the 3 are fine, but 4 breaks down into 2 and 2. So the prime factorization would be 2 times 2 times 3. So it's the factorization into only primes. Or sometimes you'll see it where you actually write the 2 times 2 as 2 squared times 3. So we'll see it both of those ways. So what we're going to do on the rest of this front page is we're going to do some factorization. The first problem, although it's large, is probably what you think of when you think of me asking you to prime factor something. You've got a number, and you're going to try and break it down into its primes. Okay, it just starts out looking like any other kind of whole number you've ever seen. So as we're doing this, I'm going to show you 2 ways to do factorization. One way is factor trees. It's commonly used. The other way is I've called it lots of things before. What should I call it today? It doesn't really have a name. But we're going to do, I'll call it a division algorithm. Kind of like we did some of the division stuff before. It looks a little bit like that, but a little bit different too. So for starters, we'll do the tree diagram. So we would break this down into any 2 numbers that multiply together to give me this value. At the absolute very least, it's even, so you know it divides by 2, but it might be easier if we start with something a little bigger than that. Like 10. Yeah, 10 at least gets us a little further along the trail. So I have 2366. So 10 is not prime, so we have to continue to break it down into 2 and 5. 2366. Something that divides it. 2. And at this point, that's probably what I would go with. In fact, that's what's on my paper too. 2. So if I divide 2366 by 2, what do I get? 1183. Okay, so 1183 is no longer divisible by 2. So let's think of something else. What would 1183 divide by? It doesn't divide by 3. How do you know? How do you check? You can add the digits together.
Oh, add all 4 digits?
Mm-hmm.
Okay, I was thinking it was the bottom.
It's all the digits, yeah, and it's common for people to sort of merge some of these properties from section 4.1 together, so I'm kind of glad you did it, because I usually don't know people are doing it until I do it on a test, and I'm like, oh no, that wasn't it. Or presentation, that's even worse, when they present it wrong. That's not good. So yeah, when we're looking at 1183, if you want to see if it's divisible by 3, you'd add the 1, 1, 8, and 3, all of it together to see if it's divisible by 3. It's not. Did anyone find one? 7 works. 13, I think, does too. Yeah. So 7 gives me 169. And then at the point when you see 169, you might recognize that one as a perfect square. Sometimes we think through that far enough in our perfect squares to get there. And we do get 13 and 13. If you had recognized 13 back when I did the 7, that would have been fine. It wouldn't be any problem. You just put there's 13 there. You'd get something besides 169, and it'd continue to break down. It is unique, the breaking down pieces, right? These prime factors are unique. There is no other arrangement that will work. This is the arrangement. One of the nice things about this tree diagram is that you get to do it sort of in whatever order you see. So if you see it's divisible by 2 and somebody else sees it's divisible by 4 on a particular problem, it doesn't matter. You can both do it. You both get the same answer. It's kind of cool like that. One of the things that's not so nice about it is that depending on how neat and tidy you are with your work anyway, and then sometimes even if you're not, even if you are neat and tidy, you have to make sure you catch the ends of all those branches. So it's really easy to sort of just overlook one of them if you're scribbling all of it down, right? If you're not being really careful. So as we look at this prime factorization, we usually list them smallest to largest. So I have 2 2s. I have a 5. I have a 7, and then 2 13s. Or if you want to, you can write it as 2 squared times 5 times 7 times 13 squared. Either of those are acceptable options. Okay, so there's nothing wrong with that. It's certainly fine. I'm not going to ask you to do it one way or another, but I do want to show you another option because it's very appealing for those of us who do tend to be on the more organized side of things, like a little bit more structure. It does that for us. So what we do is we take our 23,660, and we're going to do a division bar upside down. And we're going to divide by the smallest prime number it divides by, which would be the number 2. Okay? And you're welcome to have your calculator to do the divisions for you real quick. We're not back in section 3.5 where I need to see the division. That's not what we're doing, okay? So if I take 23,660 and I divide by 2, what do I get?
11,830.
Good, 11,830. And then we ask the same question again. Does it divide by 2, right? I mean, and it is yes, because I've got the 0 at the end, so then I go to the number 2. So if I divide 11,830 by 2, what do I get?
5,915.
Is that okay for everyone? Okay, so it no longer divides by 2, agreed? Okay, so when we are using this algorithm, we need to actually go in order of primes. Now, I didn't write my primes in order before. Maybe we should do that real quick, at least for a few of them on the top of the screen. Good grief. So 2, and then 3, and then what? 5, 11, 13, 17, 19. We may end up sometime needing more. We don't on this problem, so I'll stop. But that would be the numbers in order. So 2 does not divide the 5,915. Will 3 divide it? No. If you add that together, it is not divisible by 3, so we skip over 3. Will 5 divide it?
Yes.
Yep, so we go to 5 next. So what is 5,915 divided by 5?
1,183.
Very good, 1,183. Okay, will it divide by 5 again? No. And notice I don't have to go backwards in my list of primes and say, oh, will that one divide by 3? No, it won't, because the previous one didn't divide by 3. I am done at this point with 2, 3, and 5. So we would move on into 7, and you check 7. We know from doing the problem earlier that 7 works, and that it's 169. And then at that point, if you recognize it's 13 by 13, that's great. If you don't, you try 7 again. It would fail to work. You try 11, it would fail to work. And then when you try 13, it would work. So there's this sort of natural progression with this that appeals to those of us who are a little bit OCD. That's me. I feel like that a lot of the time. My kids feel like that a lot of the time when I tell them that something they've cleaned up in the house is not really clean, right? They do. But there's a really nice thing about this, even if you're not OCD, that's really nice, is that all your answers are in a row, in order on the outside. And that's really nice, even if you're not OCD. Yes?
Why would we finish it out by being like 13 divided by 13?
So we're done when we hit the prime number.
Okay.
13's already prime.
Okay.
That's why. Yeah, so our goal is not to get a 1 at the end, which, I mean, it could be, but our goal is just to end up with any prime number at the end. So we can see our numbers in order here. I have 2 squared times 5 times 7 times 13 squared. Or you can write them all out individually if you wish. So one of the things that's interesting about teaching is you see overlaps in your teaching of your classes. Even when they aren't even related topics, it's very interesting. And you'll see it between your professional life and your personal life as you work your way through teaching careers too, for those of you who do end up teaching and or having children or both. The overlaps are super crazy. So this is actually an example of an overlap that's occurring in my college algebra class right now. So, or intermediate algebra. Intermediate algebra class. So this is an example of one where it's partially factored, right? It's not the original number all written out to begin with. It's partially factored. So it would be counterproductive to distribute and multiply this all out into a big long number. Okay, so our goal is not to make things worse and then make things better. They're already sort of at this in-between weird, like why did they stop their state, perhaps you're thinking, but they're partially factored. So we don't want to make the mess bigger to clean it up. That's not necessary. So as you're looking at these numbers, there's really 3 factors that we need to factor further. There's a 16, an 81, and a 6. So we're going to use each of those individually, and I'm going to use that division algorithm that I just did, just so you can see it a few more times, because it's probably the least familiar to you from those 2 options over here. And we're going to do that with 16, 81, and 6. So smallest prime number that divides 16.
2, 4.
2 first, 2, and I get a 8. And then 2, and I get 4, and then 2, and I get 2, and I'm done. So my prime factorization for 16 is 2 to the 4th. We're going to do 81. Smallest prime number 81 divides by. It's not 2, right? Will 3 work?
Yeah.
Yeah. 8 plus 1's 9. 9 divides by 3, so 81 will as well. Okay, so 81 divided by 3, what is it?
27.
Yeah, it's 27. Which will divide by?
9.
But that's not prime.
30, sorry.
So we want to do the 3 to give us a 9. My 9 divides again by 3, leaving me with 3. So I have 3 to the 4th.
I have a very dumb elementary school question.
No dumb question. I mean, there actually are dumb questions, but I'm sure this one's not. What's your question, Gracie?
I have no idea how a prime number is a prime number.
A prime number is a number that doesn't break down into anything but itself in 1.
Oh, that's easy.
That's it.
Okay, I'm ready.
So the reason that 2 and 3 are prime is because if you tried to divide them by anything, the only thing they evenly divide by is themselves and 1.
Okay, so
Okay.
a prime number doesn't break down into anything except itself.
Right. Exactly. How about 6? What's the smallest prime that 6 will divide by? 2, giving me a 3, and we're done. Okay, everybody good with my 3 little bitty ones? 3 little bitty ones. Okay, cool. So what we're going to do with them then is that we're going to put them back in where they belong. Like 16's right here. I'll highlight it. It'll be easier. So the 16 itself is equivalent to 2 to the 4th. So inside of where 16 is, I'm going to write 2 to the 4th, but notice the 16 has a power of 4, so the 2 to the 4th will also have a power of 4. Now Now we're going to do the same thing with 81. 81 broke down into 3 to the 4th. So 81 is 3 to the 4th. And since then 81 was raised to the 4th, our 3 to the 4th is also raised to the 4th. And then our last piece, the 6, is over here 2 times 3. So I'm going to replace this with the 2 times 3. The 6 was raised to a power, so the 2 times 3 is also raised to a power. Okay, are all those substitution pieces okay? You see where all the pieces came from, all right? Okay, good. So where we're left with right now is back in what we did in section 3.3 with powers, right? Properties of powers or properties of exponents. So when we have an exponent raised to the exponent like the first one where I have the 4 to the 4th right here, what do I have to do with those exponents to simplify this? Multiply them. You got it. So we're going to take this. It'll be still the base 2. Multiply my 4 times 4 and I get 16. If that worked for 2 to the 4th, it's the same thing for 3 to the 4th, right? So that's also a 3 now to the 16. The last one is not the same property, right? I have 2 times 3 in parentheses raised to the power 6. So how can I simplify that or rewrite that in a different way? Right, 2 to the 6th and 3 to the 6th, and that was kind of a distribution property of powers over multiplication that we had. Now we're really close to done. What about this is not sort of in its polished, completed form? Yeah, there's some of them that have the same basis. Namely, I've got 2 to the 6th and I've got 2 to the 16th, both of them in there. And I have a property that allows me to combine them. What do I do to combine those two pieces into a single power of 2? You add them. And what is 16 plus 6? 22. And interestingly enough, just because of the values that were given in the particular problem we're working with, 3 has the same thing going on, right? 3 to the 16th and 3 to the 6th. So it's 3 to the 22. And that would be prime factorization. Hallie. All right, we're going to do one more example. Our last example looks a little bit different. It kind of looks like part B. I've got some things in factored form, but what about it makes it really actually different than the last one we did? There's an addition in the middle of there, right? Okay, so that's different because I've got 2 operations going on. I've got multiplication. Okay, exponents is just, a condensed multiplication. I have multiplication and I have addition. So as we look at this one, interestingly enough, it's in factored form within the individual addition pieces, right? They're separated from each other. If we only had the first half, it is in factored form. Agreed?
Yep.
Okay, so we don't have to try and break it down like I did on part B where it was partially factored and then I broke it down, right? It's actually already factored for us. So this one actually works a little bit differently. Because of the addition that's going on, we need to somehow combine the 2 pieces, again, without multiplying everything back out, because I don't know about you, but 7 to the 55th, no thank you. And your calculator cannot handle it. It's too big. It will not work. So you really don't have the fallback of, I'll just use my calculator to figure something. You can't. There's nothing in this one that allows your calculator to be useful. But what you can do is you can notice what these pieces have in common. So in particular, you probably notice that they both have a 2 in them, they both have a 3 in them, and they both have a 7 in them. Everybody notice that? And even if they didn't have all the pieces in common, they'd at least potentially have some of the pieces in common. So like, let's say, for instance, that 7 to the 55 on the last one wasn't there. Well, okay, but they'd still have the 2s and the 3s in common, right? So whatever pieces they have in common, what we're going to do is we're going to factor them out. So we have a 2. How many 2s do they have in common?
6.
That would be if you joined them together or combined them. It's 2. This is 2 times 2, and this one is 2 times 2 times 2 times 2. They both have 2 2s. It's what they have in common. So they have 2 2s in common. So I'm going to put 2 squared at the beginning. We're going to do the same thing with the 3s. How many 3s do they have in common? 4. And how many 7s do they have in common?
55.
55.
I got lost on how many 3s they have in common.
So I don't have a lot of space. Let me actually write it down over here. The first one has 5 3s. And the second one has 4 3s. So if you're looking at what they have in common, it means what they both have. They both have at least 4. So 4 is the one that they actually have in common. They have 1 in common. They have 2 in common. They have 3 in common. 4 is the most that they have in common. Okay, is that all right? Okay, I'm going to delete that part so that I have the space to work after it. What you're going to do next is you're going to put a parenthesis, and what we want to include is everything that wasn't included originally. So if you consider the 2 squared, it's completely been pulled out, right? It is no longer there. If you want to mark it out to remind yourself, feel free to do so. And then we move to the 3 to the 5th. Well, there's 5 3s, and I pulled out 4 of them, so what does that mean remain in the particular problem we started with that part of it? There's still one that's there. So there's still a 3. If it helps you write down right now, write it as 3 to the 1. There's a 3 to the 1 that still remains. And then the 7 to the 55 gets pulled out completely as well. So I don't have to write it either. This piece is done. Now, there is addition, so we need to make sure that there is an addition sign next. That is a really common mistake I see students make on this part of the problem, is forgetting the addition sign. It doesn't go away. It's still there. So we're basically trying to write down everything that didn't get pulled out. Well, the addition sign didn't get pulled out, so it's still there. How about this one, 2 to the 4th? Okay, so there were 4 2s. We pulled 2 of them out, so there are still 2 2s, namely 2 squared, that remain. How about the 3 to the 4th?
It's done.
It's done. And 7 to the 55? Done. Now, it wouldn't have to be that they just have one piece that remains with the power. They could have more than that. This one just happens to be the pieces that remain. Now, part of this is done, namely the part on the outside, which we might be able to combine something with it later, but right now it's done. The part on the inside with the addition, though, needs to be combined. So 3 to the 1 is 3, and 2 squared is 4, and 3 plus 4 is 7. So what I have now is 2 squared, I don't need that necessarily, times 3 to the 4th, times 7 to the 55, times another 7. So there's 7 to the 56. These two at this point can be combined. If at this point they couldn't be combined, like let's say that that number in the parentheses had been an 11, well, it'd just stay 11. That'd be fine. If the number had been an 8, right, a composite number, we'd have to break it down and then combine it with something appropriate. So at the end, we want to make sure that we have only prime numbers, which we do, right, as bases, the 2, the 3, the 7, and that we've combined all the bases that can be combined, which is what we just did in our last step, 7 to the 55th and 7 to the 1st. Any questions on that? Okay, so we're going to pause there today.